Okay, welcome back. So let's begin. Let me share my screen. Okay, so I think from the last lecture, we started discussing about Bayesian learning, right? Like, so we looked at various estimators starting from maximum likelihood estimation, right? Like estimator, then we looked at maximum a posteriori estimator, and then we also looked at the full Bayesian estimator. And throughout the lecture, like we had the running example of computing like the p-value of a Bernoulli, like in a coin toss experiment, right? Like so now, as I mentioned in the previous lecture, like so we will revisit some of the algorithms that we have previously learned in the course from the Bayesian like viewpoint. Okay, but before that, like I would like to give a bunch of comments about like so why Bayesian. Okay, so like one of the points that I think we already discussed before is maximum likelihood estimation can have very large variance. Okay, example, like there is the problem of overfitting if you're doing maximum likelihood estimation. Okay, now we can avoid that by going Bayesian. And also another big advantage of doing Bayesian learning is Bayesian approach actually gives us an estimate of the uncertainty of the model. Okay, so if you go full Bayesian, like you have access to the posterior distribution. Now you can talk about like how uncertain is the model based on the variance of this posterior distribution. Okay, and also Bayesian approaches usually work very well with small data sets. Okay, especially in settings like where you have very little data, that splitting the data into like train valid split itself is going to affect you because you're losing data. Like, so that's a setting where like you can actually use Bayesian method. Okay, and also another big advantage of a Bayesian approach is you can use prior knowledge. Okay, so you can use prior knowledge in a principled fashion. Okay, so Michelle, yeah, I will come to the regularization aspect very soon. Okay, so as I list here, there are several advantages in going Bayesian, but there is also a warning which you should be a bit careful about, which is basically if the prior is wrong, if you have a completely wrong prior, okay, then the posterior can be far off. So sometimes you need to have lots and lots of data to like handle wrong priors, like to move away from the wrong priors. But sometimes it could also be the case that like the prior distribution would completely exclude like the posterior that is close to the optimal parameter configuration that you want. So wrong priors could hurt you as well. Okay, so like normally like one of the difficulties in doing Bayesian learning is like you need to come up with a right set of priors. Okay, now with this little motivation, so let's actually go back to linear regression and discuss how to do Bayesian linear regression. Okay, so before we start doing Bayesian linear regression, like it has been a long time since we have seen regression. Like, so we have been looking at a lot of classification tasks in the past few weeks. So a quick recap of linear regression. Okay, so in this case, like I want to predict some y hat. Okay, x is the input, w is the parameter. Now this is normally w0 plus summation over j is equal to 1 to m wj phi j of x, right? So now this phi j is my nonlinear basis function. Okay, so now I can also write this in vector notation. This becomes w transpose times phi of x. So I have added w0 inside the w vector by using the usual trick that we normally do, right? So now let's say we are interested in modeling xi comma yi. This is my example. Sorry, target ti. Okay. Now this target t is generated by using some function y and an extra Gaussian noise. So we are going to assume that there is a Gaussian noise to some deterministic function y, and this is my source from which I'm generating the like a data set. Okay, so now this epsilon is a Gaussian noise with, let's say, 0 mean and beta precision. Okay, so 1 by beta is the variance. Okay, now since I'm adding a Gaussian noise to the y, right? So now I can now I can treat t to be random, right? So now what is the probability of t given x, w, and beta, right? Now I'm adding a constant term to a Gaussian noise here, right? Like, so this is deterministic term, the constant, and then like I'm adding it to, well, it's not a constant, it's a deterministic function, I'm adding it to a Gaussian, right? Like, so now this probability of t given x, w, beta is going to be a Gaussian again, okay? And this Gaussian, can someone tell me what would be the mean of this Gaussian? So epsilon is 0 mean. So what would be the mean of the Gaussian probability of t given x, w, beta? Y, right? Okay, that's the right answer. So this is going to be y of x given w, comma, beta inverse. Okay, now this is for one example, right? So now I can actually do this for the entire data set. So let's just call this scripted t and scripted x to be all the n examples, okay? So now this is given by product of n is equal to 1 to capital N, all the n examples, the Gaussian of Tn given W transpose phi of xn, which is my y of x, comma beta inverse, right? So now this is the likelihood term of the data. Okay, now if you remember, in the case of linear regression with basis functions, I can basically increase the number of basis functions, okay, to increase the model capacity. So as I increase the basis function, like as I increase the number of basis function, the model is going to have more and more capacity. Or in other words, if I have 100 basis functions, I have 100 parameters, 101 parameters, right? Like, so if I have 200 basis functions, I'll have 201 parameters. So we can actually, simply by increasing the number of basis functions, we can increase the capacity. And we also discussed in the beginning that, like, if you have more capacity, then you could overfit, right? So now this raises the question, which is how to choose the number of basis functions. Well, we have already answered this question in detail, like in the beginning of the course, but can someone tell me like how to pick the right number of basis functions? Chat or hand raise. So how do I know which is the right number of basis functions to use? Yeah, so as Krunal says, like you could do validation here, right? Like, so yeah, I think all of you are coming up with the same answer, which is try different numbers and use the validation performance. Now that is a good idea. Like, is there a, okay, so solution one, try different number and do model selection with validation set. Is there any other solution that we have learned already? Regularization, right? Like, so solution 2 could be to have a huge number of basis functions and do regularization. Now you have to tune the regularization coefficient. So you will tune this by using the validation set. Okay. So now both these solutions that we have learned so far requires a separate validation set, right? So now this has a couple of disadvantages. First of all, it is computationally extensive, right? So you have to try different values of hyperparameter for regularization term, or you have to try different number of basis functions. And this is going to be computationally expensive. You're running your experiment again and again for multiple times, right? The second of all, as I said, when you are in a low data regime, like so where like you have very few examples, then it might be a waste of valuable data that you have. Okay, so now there are two reasons why we might not prefer a validation set. Like it's computationally expensive to do model selection, or like we don't have a lot of examples that we can't afford to have a validation set. Okay, so in that cases, so how can I find the right number of basis functions? Okay, so how can I find the right capacity for model without using a validation set? Okay, now this is the question that we will try to answer like in today's lecture and probably also in Monday's lecture. Okay, now before we get into the discussion, like so a quick note. Okay, now it is also very important that like what is your choice. Okay, so the choice of basis function also matters. If you choose a wrong type of basis function, then it could hurt your performance. So to decide the overall behavior of the model, the choice of basis function also matters. But for now, like we will just go with Gaussian basis functions and like do our discussion. We will get back to the question of what type of basis function should be used towards the end of the lecture. Okay. Now there is also another question, which is, okay, now I'm interested in finding the right capacity, right? Like, so now the next question is, can we decide the model complexity by maximizing the likelihood function? So normally, like we would have a separate validation set and do model selection. Now I say you that I don't want a validation set, like I want to just use the training set. Then the next question is like, can I just decide the model capacity by maximizing the likelihood in training set? So can I? Oh, the model capacity just means like the number of parameters that you have in your model. So can we decide the model complexity by just maximizing the likelihood function for the training set? Yes, no. Well, maybe no is not an answer. Okay, yeah, so it's a no, right? Like, because like, yeah, you will overfit. So like, for example, like we have already discussed this as well. Like, so the reason why we went for a validation set is like, because if you're just trying to find the right set of hyperparameters by using your like training performance, then like the best performance will be when you have no regularization, right? Like, so when you have no regularization, that is when you have the best performance and you can easily overfit. So that is also not possible. Okay, now what else can we do? So this is where like we are going to discuss about Bayesian treatment of linear regression. Okay. Now this Bayesian treatment, as we will see later, is going to avoid the overfitting problem of MLB. Okay, and this also leads to automatic methods for determining the model complexity using just the training data alone. Okay, so that is very interesting. So we can find the best complexity for the model by just using the training data. Okay, okay. Now to do that, let's get into the prior and posterior setup, right? Like, so now we have a likelihood function, probability of t given w, which is a Gaussian, right? So now this is basically t is the vector of n targets. So this is like the joint likelihood for the entire training set. Okay. Now, what would be the best conjugate prior that I can use for my parameter w, so that I get tractable posterior? So what would be my conjugate prior for this likelihood? Do you guys remember the answer from previous lecture? Also a Gaussian, right? Like, so if you remember the previous discussion, conjugate prior of Gaussian is a Gaussian. So it's going to be a Gaussian. Okay. Now let's say P of W is my prior. Now this prior is given by some Gaussian, okay, over some mean M0, some covariance S0. Okay. We don't know what these mean and covariance are. Okay. Now we have the prior, we have the likelihood, we could compute the posterior, right? Like, so the posterior is given by P of W given T, which is simply P of T given W, P of W by P of T, right? Now, so what would be the functional form of this posterior? So what kind of distribution this posterior will be? Well, normally you have to do the derivation, right? Like, so you have to substitute, like, what is P of T given W? You have to substitute the P of W. So this is a Gaussian, this is a Gaussian, and there is a normalization term. And you do all the simplification here. So what would the end result be? Gaussian, right? Like, so that was the whole point of using the conjugate prior. So we are going to get a posterior, which is also a Gaussian. Okay. So now let's say the posterior, which is also a Gaussian, but it's going to have different mean and variance, right? Like, it's going to have some mean, let's say Mn after seeing n examples, and Sn after seeing n examples. Okay. Now, for the purpose of this lecture, I'm going to directly write what is Mn and Sn. Okay, so now if you do this tedious derivation of substituting P of T given W, P of W, in, like, multiply them, like you're multiplying two Gaussians, and like, so there was a reading on Gaussians once, right? Like, so when you multiply two Gaussians, you get a Gaussian again. And now the mean here is given by Sn times S0 inverse M0 plus beta times phi transpose T. Similarly, the covariance is given by this. Okay, now, how did I come up with this specific Gaussian? So I'm going to leave this as an exercise to derive the mean and variance by just applying Bayes rule. Okay, but for now, the derivation is not very important. Let's say we have this posterior already. Okay. Now this is a Gaussian, right? Like, so we know that in the case of Gaussian, mean is equal to mode. So my W map, or in other words, the maximum a posteriori solution for this Bayesian linear regression model is simply MN, the mean, right? Okay, now this is in general form. Okay, so now let us actually take a very simple form for simplicity. Okay, I'm going to consider a very simple prior, which is a Gaussian with zero mean and alpha inverse I, like a scalar alpha inverse I Gaussian, like variance. Okay, now then in this case, if I do the same derivation, probability of W given T is going to be some Gaussian, right? Like, so it's going to be a Gaussian. Now this Gaussian is going to have a mean, which is just this, and a variance, which is alpha I plus beta phi transpose phi. Okay, now this is for this specific prior. Okay, now before we see an example on how to use this, like a couple of notes. First, if we consider an infinitely broad prior, okay, so then in that case, the map estimate is going to be equivalent to the maximum likelihood estimate. So if we consider an infinitely broad prior, so what do we mean by infinitely broad prior? So S0 is going to be alpha inverse I with alpha tending to 0. Okay, then the mean Mn of the posterior distribution actually reduces to the maximum likelihood estimate WML. Okay, now this is equivalent to saying if I have a uniform prior, then post map estimate is equivalent to simply the MLE estimate, right? Okay, then the next simple note is like if N is equal to 0, then the posterior reverts to the prior. Okay, now the beauty of having these conjugate prior is once I see some 10 examples, I get a posterior distribution. Okay, now this posterior will actually become a prior for the 11th example. Okay, so if data arrives sequentially, okay, then the posterior distribution at any stage act as the prior for subsequent data point. Okay, and finally, something that I already just like briefly mentioned in the previous lecture, which is basically like if you look at the log of the posterior, which is nothing but log likelihood plus log prior, right? So now the ln P of W given T. So if you derive, like if you just substitute log of P of T given W and log of P of W, then you would get minus beta by W summation N is equal to 1 to capital N T of N minus W transpose phi of Xn the whole square minus alpha by 2 W transpose W plus some constant values. Okay. Now, you can actually see here that doing maximum a posteriori estimation for linear regression, so I will be maximizing this, right? Now, if you remember what we were doing in L2, like least squares with L2 regularization, we were minimizing the negation of this, right? Like in this case, there's a minus here. So this is actually equivalent to least squares with L2 regularization. Okay, So the lambda for the L2 regularization is nothing but alpha by beta. Okay, so now this is the Bayesian view of regularization. So you can see that doing maximum a posteriori estimation automatically regularizes the data, like to regularizes the model, and it is doing it in an elegant way that like you don't need to worry about tuning your like regularization coefficient. Okay, okay. Now let's actually see a small example. We are going to see a simple line fitting example that we have seen in the beginning of the course. Okay, so we're going to see the straight line fitting example. Okay, so for that, like I have generated a data set which is basically w of x given w is equal to w0 plus w1x. It's just a line with two parameters, w0 and w1. Okay, and I'm going to generate some synthetic data myself, and this is based on the function a0 plus a1x, where a0 is equal to minus 0.3, just for example. Okay, now this is my data set. Now given a bunch of examples generated from the synthetic data, I want my model to recover these two parameters, minus 0.3 and 0.5. Okay, now the way in which I'm generating this data set is like, first I'm going to sample uniformly the x from -1 to 1. Then I will evaluate f of xn comma a. Okay, so then I will also add a Gaussian noise with some standard deviation 0.2 to obtain my t of n. Okay, now the goal here is to recover a0 and a1 from the data. Okay, now for simplicity of our example, like we are going to assume that the noise variance is known. I will set beta is equal to 1 by 0.2 square, which is 25. Okay, and similarly we will fix alpha is equal to 2, the variance of the precision of the prior Gaussian. Okay, now in this case you can actually see what happens here. Okay, so first I started with my prior. Now this is a standard Gaussian prior. You can see that it is like circular, right? Like so, like it's the standard 0, 0, 1 kind of. I think in this case it is normal of 0 comma alpha inverse I, right? Right. So now if you sample a w like parameter from this prior and draw like sample a bunch of parameters from this prior and draw lines, you can actually see that the lines are all around, right? So you can see that it's a uniform prior, so it's drawing lines in any way it wants to. Okay, so now we are going to see one example. Okay, so we are seeing just this one example. Now this is the likelihood for that example, and the posterior is nothing but the multiplication of prior and likelihood, right? Like so if you multiply these two things, you get this posterior. Now you can see that just after seeing, now you sample from this posterior, and you see that like just after seeing one example, all the lines that you're sampling from this posterior passes through the circle, right? So there's a question, is alpha and beta are not hyperparameters? They are hyperparameters, I'm just fixing them. Okay, so now after that I see the second example. Now this is the likelihood for the second example. I multiply the likelihood with prior, the previous posterior, which has now become a prior, and this is my posterior. Okay, now you can see what is happening here, right? Like so this is a line, so just two lines, like two examples are enough to fit a line. So just after these two examples, you see that all the lines are converging towards the original line, right? Like so in the figure you can actually, I don't know if you can see, like there's this plus, white color plus symbol, that is my true parameter, and you can see that the posterior is already converging towards this true parameter. Now after a lot of examples, you can see that the model has almost converged close to the posterior, and the lines are actually very close to the actual line from which the data was generated. Okay, so now this is how Bayesian linear regression works. So any questions so far? Any questions? Krunal?
So if alpha and beta are hyperparameters, then wouldn't you need training validation set to fix them?
Okay, that's a good question. So you can also learn these alpha. Okay, so here's the thing, right? Like so when I use a prior, so okay, so normally like you would fix. Okay, so that becomes part of selection of prior. Okay, so normally when you choose the prior, you would be okay, maybe I'll separate these two things. Okay, so now there are two things here. Beta is part of my model, right? Alpha is part of the Gaussian prior. Okay, now in some sense this is a hyperparameter of the prior, right? So now you can have, for example, like if you want to go deep, you can have a prior for this alpha parameter. So then you have you could probably call it as a hyper prior. Okay, so now you could do all these complex things, but normally, like instead of having a separate validation set, or instead of like going deep in prior space, like so you would choose a general enough prior, with the hope that it is not like you don't do a lot of tuning for this. But as far as with the beta term, you can actually learn it along with your like Bayesian regression model. It is just that we are not doing that because it's a bit more involved. Does that answer your question?
Yeah. Thanks.
Okay. Okay. So, any other questions? Okay. So now this is fine. Like this is giving me the lines that I am interested in. Like this is only giving me a posterior distribution. Okay. Right. Like so far I get a posterior distribution and I sample a bunch of lines from the posterior distribution. But if you remember, our goal is not to compute the posterior distribution. Our goal is actually to make a prediction for a completely unseen example, right? Like so what we care about is actually the predictive distribution. Okay, so in practice, we are not just interested in the value of W, we are actually interested in making P of T hat given the entire training set, alpha and beta. Okay, so now this is my training data, and this is some new data point. Okay, now this is given by, we have already seen this inference step in the previous lecture. This is nothing but integral P of T hat given W beta, P of W given T alpha beta. So I'm just putting a scripted T to tell that like it's the entire data set, DW. Right? Now we are in a conjugate space. So like it's all good. Like, so we can actually compute a closed form solution for this. Okay. So in this case, this is a Gaussian. This is a Gaussian. And what you are essentially doing here is convolution of two Gaussians. Okay. Now, convolution of two Gaussians is also a Gaussian. So Gaussian distribution is such a easy distribution to work with. Like it has several such nice properties. Okay. So convolution of two Gaussians is also a Gaussian. Okay. So now I believe that in your Gaussian distribution reading, like you you might have seen all these derivations. So we are not going to do the derivation for what is the convolution of two Gaussians. Okay, we are just going to take it for granted. So P of t given xt alpha beta, okay, is also a Gaussian. Okay, now this Gaussian is going to have the mean as this and the covariance as this. Okay, where the covariance is, it has two terms. The first term is 1 over beta. The second term is phi of xt s and phi of x. Okay, so again, if you want as an exercise, like you could start from here and derive this. Okay, but you could also see the properties of Gaussians from Bishop, and like you would have a direct formula to do this. Okay, so now we don't care about the derivation here. Like, so what we actually care about is like, what is this variance looking like? Okay, now you can see that it has two terms. The first term is actually the noise on the data. Okay, on the second term is the uncertainty associated with parameter W. Okay, so now you can see that because the noise process and the distribution of W are two independent Gaussians, their variances are additive here. Okay, they are not having any complex structure, they are just addition of two variances. Okay, also, as you see more and more like data, the variance of this model is going to reduce. Okay, now sigma of n plus 1 square of x is actually going to be less than or equal to sigma n square of x. So as you see more and more data, now this variance is going to reduce. Okay, now as n tends to infinity, okay, one of these two terms is going to go to 0. Okay, now we are going to do a small poll here. So the sigma n squared term has, the equation has two terms. Okay, now as you see infinite amount of data, one of these two terms is going to go to 0. So press A for 1 over beta and press B for the second term. So which of these two terms is going to go to 0? A for 1 over beta, B for the second term. Okay, I'm going to stop the poll. Okay, so, well, I'm disappointed with 35% of the class with said 1 over beta. Okay, so why? So we had our whole discussion on like the concept of irreducible error in the data, right? Like, so now this is actually noise on the data. So this is the inherent noise in the data generation process, and this, you can never reduce this. In some sense, this is the irreducible like it's sometimes the irreducible error, irreducible variance in the data, right? Like it's the inherent variance of the data. So only the second term, which is actually the uncertainty associated with the parameter, is going to reduce as you see more and more data, and as n tends to infinity, the second term actually goes to 0. Okay, so now we can actually have an example for, like, we're going to do an example for this by using our like the very old sine data set regression problem. Okay, so in this case, the green curve is the sine curve that we are interested in fitting. Okay, now I'm using a bunch of Gaussian basis functions for this example. Okay, and you can see that just after seeing one example, the red line is the mean of the Gaussian. The red line is basically the mean of the Gaussian prediction. Okay, now you can also see the corresponding variance in every time step, like in every x step. You can see that when it has seen some data set, like data point, its variance is smaller. But in regions where it has not seen any examples, the variance is too high. Okay, now you can see that after seeing two examples, Now the variance around these two examples is low, but the variance around the rest of the example, like rest of the space, is still high. Okay, now you see 4 examples here. The curve is getting better. And as you see more example, you can see that the curve is approaching the green curve, and also it has very less variance, right? So now what do we observe here? So the first observation here is the predictive uncertainty actually depends on X and is actually smallest in the neighborhood of data points. The regions where I have seen some data, my variance is reducing, okay? Also, as more data points are observed, the level of uncertainty decreases. Okay, so now this is, in this case, like the green curve is actually drawn by computing the per X posterior. Okay, now we can also do another thing, like after seeing, like just like how we drew lines from sampling from the posterior, I can do the same for this sine curve data set as well. So that is what I have done here. So you can see that initially I see only one example. Maybe I should use a different color to highlight. Initially I have seen only one example, and you can see that with one example, if I sample from the posterior, I get all random curves, right? Then I see 2 examples. I see the second example. Now, if I sample from the posterior and draw these lines, you can see that it's random everywhere else, but around the region of these 2 examples, it is behaving well, right? Now, here I see 2 more, so there are totally 4 examples. Now, you can see that these curves are behaving well in the neighborhood of these data points, but in the remaining places, it's very wild, right? So now with more examples, you can see that the curves are actually the posterior. Any curve that I sample from the posterior is very close to the green curve, right? So as I see more and more examples, Bayesian linear regression automatically converges to a posterior from which I can actually get like almost good predictor. Okay, so any questions about this? Okay, if there are no more questions, okay, so now that we have seen Bayesian linear regression, like I would actually go back to the question that I asked in the beginning, which is the choice of the basis function. Okay, so now first we are going to discuss the limitations of Bayesian linear regression with Gaussian basis functions, which is what we are currently doing, right? So to recap, what is a Gaussian basis function? It is nothing but phi j of x is equal to sigma of x minus mu j by s, where mu j and s are some hyperparameters, right? Like, so this is not really an interpretation of Gaussian. It is just like looking like a Gaussian. Okay. Now, the Gaussian basis function is a localized basis function. Okay. Why? Because you choose the mean and variance, then in the data X region, like you would pick this place to be the mean for the first Gaussian basis function, this place to be the mean for the second Gaussian function, and this place to be the mean for the third Gaussian basis function, and so on. Okay. Now the main limitation of the Gaussian basis function here is if you look at regions which are not covered by these Gaussian basis functions. Okay, now you have to be very careful about picking the mean for the Gaussian basis function. For example, like if I pick all my mean for the Gaussian basis function in this region, and I don't have any basis function in this region. Okay, now in this case, the second term in the variance, right? So if you go back to the second term in the variance, now this is going to be almost close to 0, okay? Because since the Gaussian basis function is localized to that particular region and it doesn't have any It has never seen this region, like none of the basis function has seen this region. So then the second term in the variance goes to 0, and it leaves only beta inverse. Okay. So now this is a problem. This is a problem because the model will actually be very confident, like with a very less variance, in regions, okay, outside the regions occupied by my Gaussian basis function. Okay, now this is a bad behavior because the model is highly confident in region it has never seen before. So you would think that the model has highly accurate prediction, but it might be a completely random prediction. Still, the variance would be very less, that you would think that the model is too confident. Okay, now how can we avoid? So how to avoid this problem? Okay, now probably I would stop here and we will discuss how to avoid this problem in the next lecture. Okay, now just to give you something to keep thinking about. So the problem is, like, when you have a model, like when you have a Gaussian basis function based model where like the basis functions are covering only one part of the region, and you have some part of the region where you have never seen any basis function. Okay, so I can also give you more easy example to visualize. So let's say the original function is something like this. Okay, and I have basis functions only here and here. I don't have any basis function here. Okay, so then if you look at the posterior sampling from the Gaussian base, like from the Bayesian linear regression, you will see that the model has, like, for example, let's say I have seen these data points so far. Okay, now in this case, my model would have reasonable variance here, okay, and a reasonable variance here because it has seen something. Okay, now ideally it hasn't seen anything in this region. Like I have seen only 4 data points. In ideal situation, I want this variance to be so high, right? But normally that doesn't happen, and the model would have some weird, or okay, maybe let me draw a completely wrong. So the model might have a completely wrong model here, but with very low variance. Now this is what the problem I'm mentioning. So now I don't want my model to be overconfident in regions where it hasn't seen any examples. Okay, now how to avoid this problem is what we will discuss in the next lecture. So we will stop here. Any questions? As a reminder, so whatever we cover until next lecture is what we will have for the exam. So the last 2 lectures are not part of the interim, but they are useful. Like, so the second last lecture is going to be tips and tricks for doing machine learning. And the final lecture is going to be, we'll talk about frontiers and interesting problems in machine learning that you could look forward in the future courses. Are these methods only used when we don't have a lot of data? That's a good question. So normally these methods are also computationally expensive. So yes, you will often see them shining in low data regime. But Bayesian learning by itself is a whole subfield. So there are people working on scaling up these algorithms for large data regimes as well. So, but probably definitely that's out of context for the course. Yeah, so MLE is not a Bayesian approach, map is. Because in MLE, you are just maximizing the likelihood, but in map, you are maximizing a posterior distribution. Okay, so I will stop the recording.